Hello, this is Keith Graham from Codasip. In Assignment 5, Checkpoint 1, I'd like to show you how to use your add-I assembly test to validate your ITYPE data path. Now, the first thing you need to make sure before you start the checkpoint is that you have a complete software development kit for both the IA, Instruction Accurate Model, as well as the CA, Cycle Accurate Model. Now, with both of those built, I'm going to switch over to the workflow. The first thing I need to do is assign the IA model to my add-I assembly test so that I actually can compile it. I need to go to the compiler configurations, and I need to make sure I have no startup or default libraries set and save. Now with the configuration window closed, I know that's completed. I'm going to hit compile. You can see that I've compiled correctly down here. Now I'm going to do launch debug. Before I do launch debug, I need to go switch my assign SDK back to my CA model. In later versions of the software, you might be able to select the CA model directly from the launch debug command. So now I'm going to go click on, well, first of all, debug configurations. I'm going to stop at startup at after 0 instructions. That is now saved because the window has closed, and now I'm going to launch debug for my CA model. So I'm in the debugger, and the call stack actually tells you exactly which file you're in or where the breakpoint or the debugger is pointing to. So I'm pointing to add-I.s, my assembly program, line item 21. You are going to want to have the architectural registers expanded so you can see them. And to the right, in the main window of the program, you're going to see some comments that are not as indented as much. For example, on line 26. I did that to signify at that line or that comment, a particular register in the register file should be updated. So it will help you verify whether your ITYPE or RTYPE data path is working. Now, if you look at this, in the very first cycle, my instruction is going to be in the instruction fetch. Then it's going to be the second cycle, instruction decode, third execute. Then I'm going to be memory stage, write back. And the next cycle, because I'm actually storing the data in the register file at the rising edge at the end of the register file, or write back, that's when I'm going to see it written into the register file. So I'll be able to see it in the register view when I get to line 26. Let me step through this so you can actually see that. So I'm at line 26, and you can actually see I've updated the value in the register file. Now I want to show you something else here, because it's very helpful when you're doing debug, is also to take a look at the microarchitecture. Now if you think of it, the second operation right here is in the decode stage, because the line 25 would be pointing to while it's in the instruction stage. And then line 26, I haven't done line 26, so I haven't decoded it yet. So I'm going to click it one more time, which means that I've done the instruction decode of line 20 of the instruction line 25, and now I'm in the execute stage. Now, if we take a look at this, on instruction 25, I should have a -1 operand, because I have an immediate value of -1. And I'm taking the value of 2, so this should be another operand. And then I'm going to be doing that operation. So if I scroll down the microarchitecture registers, I want to look at the ID instruction decode EX pipeline registers. Remember, ID means the input of that pipeline register was the instruction decode stage, and the EX is the output is the execute stage. So if I take a look at this stage, I can see that my source 1 value from my register file is 2. And we can validate that by looking at the architectural registers. It was a value 2, because we can see that in the code as well. Now, we can also see that the immediate value coming out that was generated as immediate value is the value -1. That's all F, that's -1. Now, a couple other things to take a look at. I'm passing along an operation ALU op1, which I know that is an add operation, so I'm doing an add. And then another thing to take a look at is the reg write. That bit is 1, signifying that when it gets to the write back stage, I will perform a write to the register file. Now I'm going to click it one more time, go down one more time. Now this instruction should be in the memory stage. Now if I look at my EXMIM pipeline stage, I can see that a couple things. My destination register is 2, which matches this instruction. I am going to do a write still, so I've passed the reg write from the execute stage into the memory stage. And you can see that my ALU result is 1, which it should be, right? I'm actually saying my value is 2 plus -1, so my result is 1. So you can see that I've passed the reg write. To validate that the reg write afterwards, see, we got reg write. Here is the cycle behind the execute stage is 0 because I'm trying to write to the 0 register, which you can't do. So I always disable the reg write. Now if we go one more clock cycle, now this operation should be in the write back stage. And if I look at the MIM-WB, the pipeline register from memory input to the write back stage, as an output, you can see my destination is register 2 now. My result is 1, and I have a reg write as 1, so I'm going to write that value into the register of 1. And so if I click it one more time, you can see through the comments that X2 should now become 1. And if I scroll up and look at the architectural registers, X2 is 1. So that's just a quick video to show you how you can use the architectural and the microarchitectural registers to help validate your design as well as help to debug your design. Good luck!